Today I'll be discussing defects in solids. This portion is particularly important for understanding semiconductors later on. So, solids, or particularly crystals. The first thing that comes to our minds when we think of crystals is a perfectly repeating array of ions. But in reality, this array or lattice is not that perfect. To understand why, we have to go to the formation of crystals. These imperfections are called defects. So, going back to the formation of crystals, when crystals are formed from gaseous atoms, there are two major things that happen. Firstly, a lot of heat is lost, which is called the heat of formation. And secondly, there's a huge change in entropy, because in the gaseous form the atoms are free to move about as they please and their state is disordered, but when they form the crystal lattice they get fixed to specific points, and so the entropy decreases immensely. We all know that for a spontaneous process the entropy of the system should increase. In that case, why do crystals form at all? They shouldn't be forming because of this huge decrease in entropy. The reason is that a balance is achieved between enthalpy and entropy. Enthalpy in the form of heat of formation, that is the heat which was lost, and entropy in the form of disorderness in the crystal as crystal defects. Now these defects can be of various types because of the absence of ions or presence of excess ions and so on. Defects can be of two major types, stoichiometric and non-stoichiometric. So the stoichiometric defects are of two types again, Schottky defect and Frenkel defect. As I have shown in the diagram, the first diagram which you can see now is the Schottky defect. It is a crystal lattice which has been represented in the figure, and as you can see, both one anion and one cation are absent from the crystal lattice. That is basically the essence of Schottky defect. An equal number of anions and equal number of cations are absent from the crystal lattice. This is common in certain compounds such as NaCl. The next type is the Frenkel defect. The Frenkel defect has been represented, it is common in certain compounds such as AgBr, and in case of Frenkel defect, the size of the anion and the cation should be such that the cation can get accommodated between two anions. As you can see in the crystal lattice, one Ag plus is missing from this crystal site and it is present over here interstitially. So basically in the Frenkel defect, one or more cations are absent from their specific sites in the crystal lattice and they are present interstitially. So the size of Br minus should be such that it can accommodate the presence of another Ag plus in between two such ions. So these are the stoichiometric defects. Now moving on to the non-stoichiometric defects. First of all, we need to understand what are non-stoichiometric compounds. In case of stoichiometric compounds, there is a specific ratio in which the anion and the cation are combined. For example, in case of, let's say, AgBr, one atom of Ag plus combines with one atom of Br minus. So it's a fixed ratio. But in case of non-stoichiometric compounds, this ratio is not fixed. For example, in case of FeS, it seems that one atom of Fe is combining with one atom of S, but in reality the amount of Fe varies. That is, it is not exactly one atom corresponding to each S. Now, in case of non-stoichiometric compounds, there are two major kinds of defects. Firstly, the kind of defect which is observed in compounds which have more than one stable oxidation state. For example, FeS, FeO. It has been represented in the figure. See, FeS has been written as Fe 1 minus delta S. Here delta represents the fraction of vacant cation sites per formula weight. So the electrical neutrality in this case is maintained by oxidizing the equivalent number of Fe2 plus to Fe3 plus. So in this compound FeS, there are a certain number of ions which are Fe2 plus and a certain number which are Fe3 plus, depending on how many are required to maintain the electrical neutrality. As you can see in this metal defect, one Fe is absent from the lattice site. So, and still the compound overall is electrically neutral. This is possible because of the fact that Fe has two stable oxidation states. It would not have been possible otherwise. So that is one kind of defect, and the other kind of defect has been represented below. So this is for the second type of non-stoichiometric compound where the metal does not have more than one stable oxidation state. For example, in NaCl, Na has only +1 as the stable oxidation state. Then how is it possible to have this non-stoichiometric compound? It is possible because of the varying number of Cl minus atoms. So essentially, as you can see in the crystal lattice, one Cl minus has been replaced by an electron. Since Cl minus has 1 minus charge and an electron also has 1 minus charge, the electrical neutrality of the structure is maintained. So this is one kind of defect. So overall, there are two types of stoichiometric defects that you need to know about and two types of non-stoichiometric defects. Understanding these defects, we can then move on to the next part of the chapter, which is semiconductors, metals and insulators.